In this problem, we're asked to find the reactions for this frame. If we look at this frame, it has a fixed support, a roller support, and two internal pins or internal hinges. So this makes the problem relatively difficult, where we'll need to take some section cuts in order to solve for it. So first off, if we draw our summary or our free body diagram for the global structure, we see we have three reactions at A. There's an RAY missing here, or RAX missing, RAX reactions. Our pin, a 15 kilonewton load, RBY and RCY. The rollers only put a single reaction force on the beam. So if we count the number of reactions, our number of reactions are equal to 5. This means we have 5 unknowns. And we have 3 equations to work with. These are equations of equilibrium. So we have the sum of forces in X is equal to 0. The sum of forces in Y is equal to 0. And the sum of moments about any point on the XY plane is equal to Z. Moments about the Z-axis is equal to 0, I'm sorry. Since we have 5 reactions or 5 unknowns and 3 equations, we need to make section cuts. To solve this. Now, this is a determinate frame. There are we don't need to introduce equations beyond those of equilibrium to solve for it. So in order to solve it, we're going to need to take cuts at specific locations and isolate free body diagrams of sections and look at the equilibrium of sections themselves and apply what we learned from one section to the other section and continue on that until we complete the reactions for the entire beam. So if we take a first cut, that location we'll define as A here, and we're going to cut right through that internal pin at E. So we'll cut at A and draw the free body diagram of EC, so the right hand side of the cut. And in this free body diagram, we're going to have a length of the beam. We'll have a vertical force at C. This can be called RCY. We will have an internal vertical force at the pin and an internal horizontal force or normal force at the same location. And we'll call these EX and EY. We have location E and we have location C. And these are separated by a distance of 6 meters. So we don't have any external loading here. And we can see once we begin to solve that this is a rather simple solution. We have sum of forces in X is equal to 0. This gives us EX is equal to 0. And we have sum of forces in Y is equal to 0. We should probably do sum of moments first, but we'll do this. We have EY plus RCY is equal to 0. If we take sum of moments about location E and set that equal to 0, we'll start to see something happen. We have RCY times 6. This is trying to go counterclockwise according to the way that we've drawn this free body diagram, is equal to 0. Therefore, RCY itself is equal to 0. And that's one of our reaction values, so let's put a red box around it because that's what we're looking for. So the vertical force at roller C is equal to 0. And then if we plug that back into the equation that we've solved for up here, so let's just take this equation and go down here with it, we can say EY plus 0 is equal to 0, therefore EY itself is equal to 0. So the forces in this particular member are all equal to 0, and there's not much to gather from that. Now we can apply those forces, the 0 forces still, to another section. So let's introduce another cut here, and we'll call this one cut BB. And we will now cut at BB and AA and draw the free body diagram of member DE. So we'll draw the diagram between this pin and this pin. Now, this diagram is pretty straightforward. We have a length of beam, we have a force EY is equal to 0 that we calculated on the other side of that cut, and we have EX is also equal to 0. We have a force at the cut over here of DX and a force of DY. And our 15 kilonewtons is applied, and we have a force RBY. And distances are 2 meters between our forces and supports. 2 meters, 2 meters, and 2 meters. At this point, we can apply our equilibrium conditions and take sum of forces in Y is equal to 0, and sum of forces in X, that's a sum, that's a terrible drawing. Sum of forces in X is equal to 0, and sum of moments is equal to 0. So we'll apply those three conditions. We'll start with the sum of forces in X, and we see that if we do that, we end up with dx is equal to 0. And because dx plus 0 is equal to 0. Now we can take the sum of moments about a point. So let's take sum of moments about location B. So let's put in our joint locations here. B, E, and D. And I suppose, oh, we have them on that one. So if we take sum of moments about B and set that equal to 0, we can end up with 15 times 2, going counterclockwise. So this force times the distance away. To that, we subtract dy times 4 and set that equal to 0. So then if we expand this equation and solve for dy, we can see that dy, or the internal force at the internal pin D, is equal to plus 7.5 kilonewtons. And the plus indicates that we drew it in the correct direction. And finally, if we go over here and apply the sum of forces in Y is equal to 0, we can see that we have dy minus 15 plus RBY is equal to 0. And since we solve for dy, we can rearrange this and solve for RBY is equal to 15 minus 7.5. And this gives us RBY is equal to plus 7.5 kilonewtons up. And that's one of our support reactions. So we can put a box around it, and we've solved for another one of our unknowns. Now we finished with this free body diagram, so we can take what we learned about dy and dx and apply them to the other side of the cut. So we will now cut at BB and draw free body diagram for AD, so A to D. And to that we'll apply the forces at D equal and opposite to the location of our cut. So we found them at dy acting up on the member DE. That means member DE is pushing down on member AB, or AD. We draw in our member here. We have our AY. We have our horizontal reaction at A, our AX. We have our moment, MRA. We have joint A. We have joint D. And at D, we have a force dy now acting downwards, and a dx force that we found was 0. And this is separated by 6 meters. And if we go over here and take sum of forces in x and set that equal to 0, we can see that RAX is equal to 0. So there's no x force anywhere on this frame. Next we can apply our vertical equilibrium, so sum of forces in y is equal to 0, and we can see that RAY minus dy is equal to 0. Plugging in dy and rearranging, we get RAY is equal to plus 7.5 kilonewtons. And then finally, we can take the sum of moments about a point and solve for the moment reaction at A. So we'll do that over here, and we'll take the sum of moments about location A and set that equal to 0. This gives us MRA, the reaction moment at A, drawn as acting counterclockwise, which is positive, minus dy times 6 is equal to 0. Plugging in values and solving for MRA, we get MRA is equal to 7.5 times 6. And this gives us MRA is equal to plus 45 kilonewton meters. And the plus means that we drew it correctly, so it's acting counterclockwise. It's a positive support moment. And now we can go ahead and look at our summary diagram. And here we can begin to add in our values. So we've solved for MRA, and MRA was 45 kilonewton meters. And RAX was 0. RAY was 7.5 kilonewtons. Our BY we also found here has 7.5. And our CY we found to be 0. So at that point, we've found all the reactions for this frame. And we had to take section cuts in order to do it because there was more unknowns, more reactions, than there were equations of global equilibrium.